Welcome everyone. In this video I'm going to build another instrument or device, and you could see how I unpacked it. So now I cleaned up the desk and organized most of the things, so you can see the components and the printed circuit board which I will use in this video. And the device that I'm trying to build here is a high precision milliohm meter. So it is intended to be used at an ohm to milliohm range, so it should detect very tiny resistance values. And based on the nature of this circuit, we cannot measure like conventional values like kiloohms and things like that, but we can measure ohms and milliohms quite comfortably. So this circuit is actually based on two designs which I discovered on YouTube. So this is a mixture of his circuits, and I really recommend you to visit his channel because he's very knowledgeable in electronics and he has quite cool projects. And I basically used and borrowed the ideas from Scullcom's YouTube channel. He built a milliohm meter and he also built a millivoltmeter, and I mixed these two things because I found this idea really cool, and I always wanted to build a milliohm meter because I wanted to learn the principles of it. So therefore I designed this PCB, and the main principle of this milliohm meter is that we have a current source which is located on this side of the PCB, and that current source is attached to an unknown resistor. And then obviously the resistor follows Ohm's law, and therefore there will be a voltage drop on that resistor based on the current that we produce with this board. And then we have to measure that voltage. So on this side of the panel we have a very precise 24-bit AD converter with a very reliable reference. So hopefully it will measure the voltage very precisely. And then that data is read and processed by an Arduino Nano. And then I can send it to a display, an I2C compatible display, or send it to the computer via USB. And this is the so-called 4-point method or Kelvin method. So you supply current to your unknown resistor, you measure the voltage, and based on these principles, you can determine the resistance of the unknown resistor. So this is the main principle, and then here on this circuit board I already sort of assembled the SMD components. So I put them in their proper alignment and proper arrangement. So what I will have to do is that I just pick up one part and put it on the PCB where I want to build the circuit. So it will be very easy to do everything. And as you can see, there are several through-the-hole components. Those are more or less all resistors. There is one capacitor which is also through-the-hole component, but most of them are resistors. These are precision resistors, and I will solder them manually. But there will be a certain recipe, a certain roadmap for building this circuit, because first I have to build and test the voltage regulator, and then I will have to build and test the current source part, and then I will build the voltage reference part. So I will measure the voltage reference if it works or not, and then I build the rest, which means that I build the AD converter part and its other components. And probably in the second part, because this will be very long and otherwise, I will attach the Arduino Nano and program it and show you how to juggle with the data and how to put everything on a display and send it to your computer. So that will be it in this one or two videos. And as you can see, again, I have very nice PCBs, and this is from the sponsor of the video, PCBWay. As you can see, they are now very nice white, and I really like this design because it looks very clear. And I also chose to have some of my texts written with white actually they are at the same layer where you have the copper traces, and I like it because it just shows up very nicely when you tilt this PCB, and it has a certain angle of light. So as you can see, they look gorgeous, and these panels are quite tiny, so you can put them in an enclosure very easily. And that's why I put the 4 holes on the corners, so it's easy to handle them. So PCBWay is a service provider specialized on PCB making and PCB assembly, but they also have other services like CNC machining, 3D printing, and sheet metal working as well. And now, as you can see also in these ever-changing background pictures, is that they have upgraded their PCB material from TG130 to TG150. And what does this mean? So this means that instead of 130 degrees Celsius, the material of the PCB has the glass transition temperature at 150 degrees Celsius. So it's a more temperature resistant material now, which is much better for us makers if we have some more temperature demanding projects or something soldering related stuff, and so on and so on. But to explain it in one word, they have better quality PCBs. So first of all, I have to build the voltage regulator part, and I did a bit of cheating here because I did a mistake when I ordered my parts. And actually this is not an SMD component, but I converted it into an SMD component. So this is a normal voltage regulator, not even the same type and brand which I originally wanted to use, but it has the same characteristics as my original LM2940 voltage regulator. Yeah, it comes with through the whole component packaging. So yeah, it is what it is. But first I will solder this guy here on a panel, plus some wires and also some capacitor, so I can measure the output voltage of the regulator when I feed it with 9 volts. So I will start doing the things, and I will start to show you the process. So a little fast forward. We have the voltage regulator and the capacitor in the PCB, and I connected these clamps to the input part, which will be 9 volts, and then I will measure the 5 volt rail, and I will be hoping that the voltage will be 5 volts. So let's power this up and see the voltage. So there is no current draw, as I can see on the power supply, which is good, so no short circuit. And then I just tap the ground and I tap 5 volt component. There we go, 4.952. That's pretty much 5 volts. That's what we want. So we can proceed further. We have U3 and U2. Those are the two current source components, let's say like that. One is a precision shunt voltage reference, which will provide the voltage reference for the current regulator. And then we have the current regulator, which is capable of providing 200 milliamps, but based on the resistors that we use here, the through hole components, we will provide 100 milliamps only. So that's what we have here. So now we have these two chips attached, and I used a heat gun, so I was cheating a little bit. So I was not using hand soldering. And now we have to solder these through the hole components, which are several resistors and a potentiometer here, RV1. So now the current regulator part is done, so the whole left side of this panel is done, and we have the current source wires here. So now I will find a relatively low value resistance, which I can test, and then I will test the current source part. So I just put everything back to my OmniFixel rig, and then I will connect the corresponding parts, which will be a multimeter, a resistor, and a power source for the voltage regulator. So hopefully everything will work as it should. So I put everything together, and it's a bit chaotic, but I explained everything to you. So this is the PCB which we are building now. This is a 1 ohm resistor. It's a high performance resistor because I will use this as a load, but at least it's a 1 ohm resistor, so it's compatible with this setup. And the smaller multimeter will measure the voltage, so the clamps are just attached to the two poles of this high performance resistor, and then the bigger guy will measure the milliamps. So current comes out on the red, let's say, and then goes into the multimeter, and then comes out on this black probe and goes into the resistor, and then it goes back to the circuit through the black wire. And that seems to be correct wiring, and I think I don't have any shorts anywhere, so I just power up and see if the magic smoke comes out. And nothing comes out, and we have roughly the correct values, so I just have to adjust this a little bit. But as you can see, this almost gives you the Ohm's law. As you can see it very nicely, we have 1 ohm plus minus something, and we have almost the same values here. So this is 195 millivolts and 191 milliamps. So our circuit is working. I'm very happy about it. And I can see the current consumption of the power supply, which is actually there. It's a laboratory bench power supply, and it is consuming 0.196 amps. So yeah, it's basically everything just adds up very nicely. So now the next part will be that I disassemble this mess here, and I add the voltage reference part, solder it, and then we test that part as well if we get the 4.069 volts properly. So let's go to that part. So now I put everything to the place, basically just two decoupling capacitors, one ceramic and one tantalum capacitor, and then the chip for the voltage reference. So now I will just use my heat gun and try not to burn the components while soldering them properly. So I checked if the components are not shorted, and they are not, and that was a bit interesting question for me, because I saw some tiny, let's say, balls of solder flying away when I was soldering with this heat gun, and I thought that it will go under the parts and short everything, but luckily no. So again, I will power up this device. And now we should have part of the 5 volt coming to the voltage reference. And I left the tab open, basically, for the voltage reference on purpose. So anytime I can go in with a probe and just measure the reference voltage value. So now I power up this thing. And I see no power draw, which is good because then there's no shorts. And then we measure the voltage reference value. And as you can see, for some reason, I'm measuring 1.9 volts instead of the 4.096, which is very interesting. So I will check what is happening here, and then I will troubleshoot the things. So I could not find any source for this kind of phenomena. So what I will complete the circuit, because I believe that the problem is that the reference voltage is actually not connected to any kind of load. So the circuit of it is not yet, let's say, complete. So I will add the ADC part, and we will see if it works or not. So I added the LTC2400 AD converter. So that should complete the whole ADC circuit. And now I will try to measure the voltage reference again and see if we have better luck. And yes, there it is, 4.093. So it seems that the voltage reference needs a sort of load to work properly. But now we have a working current source and working voltmeter without the microcontroller, obviously. So now I have to complete another set of SMD part, which is actually some sort of power source, so-called charge pump, which transforms the plus 5 volt power source into plus and minus 10 volt. And then we have a precision differential amplifier, which will be used to amplify the voltage which we read here. So that part comes right now. So I will solder first the SMD components because they are a bit more challenging, and then I will finish up with the through-hole components. And then we will have the complete circuit basically. So the SMD soldering part is done, and I could not find any shorts with the multimeter, so far so good. I had to clean up a little bit because I added a bit too much soldering paste, but now using this copper thingy, I was able to remove the excess soldering material, so that's fine. So now we just have 1, 2, 3, 4 components, 3 resistors and 1 variable resistor, a potentiometer, and with that the circuit will be complete. So then let's solder the rest of the things. So now, as you can see, the board is upside down, so I will solder the resistors, and then I will flip it back. I will add a few cables for the voltage sensing part. I will add these sockets for the Arduino, and I will add a few pins for the I2C display. So let's just do this quickly. So as you can see, the sockets for the Arduino are a bit wobbly, but I have a nice trick for this, which I want to show you. So we take the counterparts of these things, these jumper pins, and just plug in them nicely. So this holds it together with the proper dimensions. So now I just flip this back and clamp it with this nice clamp here. This should work. And then I just put a few points here and there, and I can continue soldering it properly and easily. So this is done. Now we only miss these 2 wires here and then 4 jumper pins here, which I will just fix. I will use this, cut down 4 pieces and then fix the wire as well and solder it. So the purpose of these 4 pins is to provide power and data connection for the I2C display. So we have ground, +5 volts, clock and data pins here. So I just used those pins and put it here. So I can make a connection and just plug it there, and that should be working simply. So as you can see, this is done now, and hopefully it will work properly. So the next big step is to connect everything with an Arduino Nano, program it so it can communicate with the LTC2400 24-bit AD converter, and then I slowly start to, let's say, start up the things. So first I will just check how the voltage measurement is working with this AD converter. So I will just supply some power to these 2 pins and see what is being observed by the Arduino, what is visible for it. And then I will adjust these potentiometers, so we trim the output values and also the input values, and that we make sure that we measure relatively precise values. And after that there's nothing else to do, just put everything in an enclosure. And I have some really nice clips for this measurement, which looks something like this. So I have 4 BNC connectors here, as you can see, and then I have the 2 clips, and then the clips are relatively special in a way that the pins, or these tweezer parts, have this double purpose, that one pin is providing one pole of the current. So let's say this is the minus current, and the other pin of this tweezer is measuring the minus voltage, and then the same goes on here but with the positive side. So let's say this pin provides the positive current, and then this measures the positive voltage. So this is just allowing us to do the Kelvin measurement easily. So then I will put everything in an enclosure once I'm done with the Arduino and I'm done with the display as well. And we will have a nice milliOhm meter in a box with a fancy OLED display. So I planned these things for the video because it's getting very long, I think. So for this it's enough just to see and show that this can be built relatively easily, and it did not take too much time. And this is my first build, so yeah, it's not too bad. I could have done a bit better job with the pins of this resistor, but now I'm not bothered by it. Maybe the next version will be a bit nicer. But yeah, this was all. So once again, if you want to get these nice PCBs, or if you want to get nice PCBs in general, please visit PCBWay's website, PCBWay.com, because you can buy nice PCBs and nice services from them. And also don't forget to visit my website, curiousscientist.tech. Link is in the description as well, because you will find all the resources, some additional pictures and so on for this project. So please don't forget to visit my website as well. And stay tuned for the next video, because then in the next video we will go for the programming part, and we will hook up the system with an Arduino, with a display, and I put everything in a nice enclosure, and we will use those nice clips, and I will measure a few things to see how this system works. So I hope this video was useful to you. I hope you found it interesting. I hope you learned something, and see you in the next video.